Yeah, no problem.
Thank you very much, Orbasi. And we're going to continue where we left yesterday. Nobody has come to me with the right answer of exercise 1 yet, so there's still a free beer. And maybe I can hike up the stake, as I don't have an answer, so I'm going to pay 2 beers. But then if I do this, maybe I should do the other way around. If you guys lose, nobody gives me the answer by the end of today, you all pay me a beer.
You are only getting beer, no pictures.
Hey, you don't count. You're not a student, Steve. Okay, so nobody has given me the answers of solution of exercise 1, and I'm not going to give it to you right now. And maybe when I finish question period, if there's not too many questions, then I'll go to exercise 1 and tell you how it works. So you still have about an hour to kind of find the solution, and the stake is 2 beers, right? Are you ready for this? Are you matching me on the extra beer? You're supposed to say something. Okay, good. I'm doing a good deal here. Okay, exercise number 2, how to make a control knot. I'm going to show it in a few minutes how to do this. So there you'll get the answer of how to do this. And there was no beer related to that one. Okay, you should remember the schedule will be changed a little bit. So there's lunch from 12 to 1:30, so I'm going to have about an hour 15. And then we'll get a few questions. Barry Sanders will be after lunch instead of before lunch. And then we'll have tea, and we'll have more lectures in the afternoon. As my lectures are food for thought, you should be impressed by this, you might skip lunch and just kind of keep on and have the lectures. Okay. You have not thrown me anything, so I assume that you're all okay, no lunch, and well, just food for thought. So let's see what we did yesterday. We talked about nuclear magnetic resonance and how we can use this to quantum computer or do quantum information processing. So I talked about what are the qubits, and what are the qubits again? I'm going to start to throw the chalk if you guys don't answer. So what are the qubits? The spins of the nuclear, the magnetic moment of the nuclear spins. So we have a molecule, and then each of the atoms which have a spin half, and we're going to go and look at the spin half, are my qubits. And it turns out that in NMR, in distinction to many other quantum information processing devices, we don't use single atoms, but we use an ensemble of them. And that makes some difference here and there, but we can still quantum compute with ensemble. And the reason that we use an ensemble is because something we haven't talked yet, the measurement, and I'll come back to this. So once we have our qubits, we want to manipulate them. And the computer scientist tells us that if they give us a quantum algorithm, we can break this quantum algorithm in a set of 1 qubit gate and 2 qubit gate. And so we have to think about how do we do 1 qubit gate and 2 qubit gate in NMR. So these qubits are addressed to with a magnetic field at a given frequency. So each of them have a frequency, omega 1, omega 2, omega 3. And if you send a radio frequency field in this direction, then we can make these qubit rotate. And by changing the phase of this field, we can do rotation around the x-axis or the y-axis. You remember there's a preferred z-axis, which is the axis which is defined by my big magnet because I put all of this in a big magnetic field in the z direction. So with this, I can do rotation around the x-axis, around the y-axis, and I can redefine the rotating frame, and this, I can use this to define a z rotation also by doing this. So with this, I can do x, y, z rotation. I can do a generic 1 qubit rotation, so we have taken care of that. We can also do 2 qubit gates. And although at the first thought we would say, oh, the dipole-dipole interaction, that's what we're interested in. But because we're in a liquid, the molecules are tumbling very fast. The dipole-dipole interaction gets averaged pretty much to 0. So we don't see it. but there's still an interaction which is left due to electrons which are wandering around. And if these nuclear spins have different direction, the electron has different energy, there's an interaction which is mediated through the electron. And this is what we're going to do. And what does the interaction look like is for 2 qubit is the form Z1, Z2. And you remember this, we can think about this. If the let's say the first qubit is in the 0 state, it's going to increase the Larmor frequency of the second qubit. If the first qubit is in 1 state, it's going to decrease the Larmor frequency of the second one. So that's how qubits have a very primitive language. That's how they talk to each other. So if you're up or down, then your neighbor is going to behave slightly differently. Okay? So that's how we go and do this. I should have mentioned also that when we talk about 1 qubit gate, we talk a little bit about RF selection. Because we have an ensemble, the gates that we do are not exactly the same everywhere in the sample, and we kind of took care of this. At least I gave you a recipe. Even if you don't understand all the details of it, you know that it is possible to take care of our RF selection. And we also use a tool of a gradient. If we have a field in this direction, which is a gradient, it labels different part of the density matrix different way, and where you're going to use this, or I'll show you how to use this in a few minutes. Okay, so what I want to do is talk about measurements. I'll do this relatively quickly. Talk about the initial state, a little bit about noise, and then I'll jump in on error correction. So the first piece of error correction will be a little bit separate than everything we've done here. So if you got lost here, then you have to wake up. At this part here, you'll learn something new. And then the new thing that you'll use this, you've learned here, you will learn here. Then I'm going to use it in an MR and show you how can we implement a small quantum error correcting code and how it works in practice. So I won't do error correction in a very formal way. I'll try to use it in an intuitive way, show you roughly how it works. And so it's a little bit like an exercise class that we're going to do. Okay, so that was my 2 qubit gate. We showed how to turn it off. That was a refocusing. And so let's go on to measurement. So how does the measurement work? So if you look at system where you have a single quantum system, and for example, ion traps or photons, you can go and measure the single quantum system. You do projective measurement and sometimes destructive measurements. Here, we make an ensemble measurement. So this measurement that we're going to do is not going to project the state in a given state, but we just take an average of it. And what are we really measuring is if the spins are in the XY plane, they are going to rotate because of this big magnetic field in that direction. And if you don't send any RF pulse, radio frequency pulse in here, and instead you're measuring the current in that coil, then you'll see a current which is induced by the spin rotating. So the spin are going to rotate in here, induce a current here. We're going to measure this. And so you're going to measure this. What you'll see is some oscillation. If there would be no decoherence, it will oscillate forever. But there's some decoherence, only it disappears. We're going to Fourier transform this current, and then we get peaks. And we get peaks at the different Larmor frequency, which correspond to the spin number 1 or the spin number 2. Okay? The observable correspond to the I minus, the absorption of a photon by the electrons in that coil. So if you look at I minus, you remember that I minus is equal to X minus IY. So you'll have a real and imaginary part. And by separating the two, you can think of the observable are either the operator X or the operator Y. So we can think about this. So we can go and measure what is the value of X, what is the value of Y, or what is the magnetization in the direction of X and Y, which means that what you're going to observe is the value alpha or the value beta while you do this. So that's how you kind of get an answer out of your computation. So when we do quantum computation with this, we first take the thermal state, for example, rotate it in the X plane. If we keep it in the Z direction, we don't observe anything. We put it in the X plane, and then we go and measure something. We get a value, which is our reference. Then we go and do our quantum computation. We're going to go and measure this again. We'll get a peak here, which will have a different amplitude, and this amplitude will be related to what is the value of alpha here. Okay, so we can go and pick up some elements in the density matrix here and there. But this way we cannot measure this gamma. So suppose that I'm asking you, go and measure gamma. How are you going to do this? So our observable are x and y, and not z directly. I've told you the answer a few seconds ago. So what we're going to do, okay, somebody gives me a hint. Doesn't matter if the hint is not correct, right? But you have to say something. Total science. Absolutely. So instead of measuring rho, we're going to make a rotation around, let's say, y by 90 degree, rho, y dagger of 90 degree. And if you do this, you remember that this looks like e to the minus I pi over 4 y. And this one is the same thing with a plus. You take the density matrix in the middle, multiply these two things. You remember when we were in the block sphere, it's going to rotate these x, y, and z because I rotate around the y-axis. I rotate around the y-axis. So let's call this rho final. The one part doesn't change because if you rotate on both sides, nothing happens. The x is going to turn into, so your y-axis, and you rotate x, you get minus z. So this becomes minus z. Y doesn't change. And this one, the z-axis, is going to rotate onto the x-axis. And so we go and measure this trace there, and then suddenly the peak will be related to this. So if I tell you, I want this piece of the density matrix, now you know how to go and find it. You just make the right rotation so that your observable turns into this. And because we have a universal set of 1 qubit gate or 1 qubit rotation, we can always turn these operators into the one that you want. We can go and measure. And if you have 2 quantum bits, you can go and do the same thing. Now, second thing you need to know is here, these qubits were not coupled. And if you couple them, then I mentioned this yesterday, this peak is going to be split in two. And this is because when you have a coupling here, if this is in state 0, it's going to add to frequency, shift it a little bit there, or if in state 1, a little bit on the other side. And so for the second qubit, we have the same thing. By measuring the splitting between the peaks, we know we can find what is the value of J. Okay? So similar kind of things here. These operators that I write here, I assume that it is what is the density matrix is. So, for example, the top of X, I assume that beta and gamma is equal to 0. I go and observe. I get a peak at some value here. Now, if I have 2 quantum bits, but I'm looking only at the first one, then I'll get, if I have X for the first qubit, 1 for the second qubit, I'm going to have these 2 peaks. But you can go and calculate what happens if instead of the operator for the second qubit being 1, it's a z, then you get this peak with a minus sign there. And so if I come with a spectrum with you and I say it looks like this, you even don't have to calculate. You say, that's an xz part in the density matrix. So you can go and measure this. And now if you add this plus this, these 2 peaks here are going to cancel with each other. You'll get only 1. Okay, which means that the second spin that you are not observing is in a state 0. And so the operator with 1 plus z, you remember that 1 is 1, 1, z is 1 minus 1. The minus 1 and the 1 cancel, so you get only the top left part of the Pauli matrix element, corresponding to state 0. In fact, I should have put a ket 0 on the other side, which correspond to the matrix element here. Now, if you have 3 qubits, and you look at the first one, then if it's x11, then instead of having 2 peaks, you'll have 4, which correspond to the splitting of the coupling with the first one, coupling for the second one. And then you can have a bunch of different elements like xzz or xz1. So if you have xz1, you could have these 2 peaks up, these 2 peaks down, or kind of up, down, up, down. And xzz will look like up, down, down, up. So by, again, looking at what the spectrum looks like, you can tease out what the density matrix is. And then if you do a state of the form like this, only this peak here, you'll know that there's the two spin that you have, they are only in the state 0, 0. And that looks like a pure state. Okay, so that's how measurements work, and we'll come back to this as you. Here's a spectrum of some slightly more complicated measurement, and you see many peaks here. And you see, so we're looking at the atom nuclei of C2 here, many peaks, because it's coupled to this one, coupled to this one, coupled to this one, coupled to this one, and this one. You see 4s of peaks, and then you can understand exactly the pattern of this just by looking at what are the values of the coupling in there. So M, okay, 2 big peaks here because the stronger coupling is here. There's a smaller one with C2 and C3, which leads to family of peaks like this. So you can understand how the Hamiltonian, the behavior of the Hamiltonian just by looking at the spectra of this. In practice, it's pretty hard to find the Hamiltonian as the number goes of qubits goes higher and higher. In one of the first slides yesterday, I showed you one with 12 qubits. It's quite complex to go and find the value of all these couplings. And in particular, the signs of these couplings is a little bit tricky. Okay, so what I want to do now is talk about initial state. So I told you yesterday, and in the notation slide, I told you that beta times omega is equal to about 10 to the minus 5. So we have a very small magnetic moment, where it's a very strong field, but a very small magnetic moment. Room temperature, 300 K, we get about 10 to the minus 5. So the density matrix, e to the minus beta h, the initial state, which is the natural equilibrium state, can be written approximately as 1 minus beta, because beta is so small of this form here, but it's a very mixed state. So if we would like to have all the spin really up, kind of in a pure state, one way of doing this is, so let's assume I have a chain of many spin. I want to put this one in state 0. There's a way to borrow the purity of all of those and concentrate it in one of them. And it turns out you could do this efficiently. That is, it takes a fixed number of extra spin to purify that one. And so you can go and do this. And this is called algorithmic cooling. I'm not going to talk more about it, except if I have more time at the end and if someone is interested, you can go and do this. So it's really the idea of cooling a spin, not by using a refrigerator of where you could put the cold things next to your hot things and cool it down, but you're looking a little bit like Maxwell's demon, where you say, oh, there are certain states which behave in a certain way, and if I manipulate them the right way, my spin is going to be cooled down. So it's a computational way of thinking about cooling the system. Okay? Now, at room temperature for NMR, it turns out that the number of extra spin that we need to make this one roughly of order 1 polarization, like essentially pointing up, goes like 1 over beta squared. If beta is 10 to the minus 5, 1 over beta squared is a large number of spins. And so totally impractical for room temperature liquid state NMR. But if we would go down to low temperature, a few degree Kelvin, field of order of Tesla, if we look at the electrons, they are pretty much polarized about order 1, but not exactly. And then we can use that techniques. And this is something that we're planning to do in the future, but we haven't done yet. So instead of doing this, we have a different way of doing it, which is one what was initially proposed for liquid state NMR, which comes with a problem. The idea is, let's make a transformation of the state, which is 1 minus beta h, so it transforms to something which looks like this, like a pure state. So there is a way of doing this, but what you do by doing this is you pay a price that the amplitude of this goes down exponentially. So if you do it this way, you're not going to gain by doing a quantum computation because you pay an exponential cost by doing this. Although you can use NMR to demonstrate certain things. And as I mentioned to you, what I'm interested in is to demonstrate quantum error correction. So in that case, we can do this for a small number of qubits and show. And here's a quantum algorithm, or kind of a quantum circuit showing how to do this. And the basic idea is get rid of the polarization on all the spin except one. So let's say we call this one Z. So you get something which is a form Z1. And I'm sorry to have written it this way, but if I would have written it the other way, they would have overlap. So you'll have a little bit of a headache, but you can follow this here. So you have Z1, you do a Y rotation, you turn this into X1. You do one of this coupling, 2-qubit gate coupling, you turn this into YZ. Another rotation goes like YX. And if you go back to the density matrix and says, how does YX looks like? Well, it looks like I plus, I minus, I plus, plus, I minus. Multiply all the terms, you'll have terms which are like I plus, I plus, I plus, I minus. If you put a gradient field, then suddenly the term which looks like I plus will have a phase which is twice the strength of the gradient field, and the terms which looks like I plus, I minus will have no field, no phase. Then we're going to undo what we've done, and what happens is that the states which will look like 0, 0 will have a phase which is twice what the state like 0, 1, 1, 0, or 1, 1 would look like. And if you undo the gradient with twice the strength, these things will keep a phase, but this one will have no phase. So these things, when we do the observation, are going to disappear, and you'll get left with this. And then that is the way that you can prepare one of these, what is called a pseudo-pure state. Okay? So in the demonstration of quantum error correction, we're going to use that trick. Now, I'm going pretty quick on this, but if you go back to the notes, go through this, it's relatively easy to show how this happens and how this works. I'm just going to make a very, very quick note here on maybe there's some neat algorithm where we don't need a pure state. And in fact, there was a challenge of about 10 years ago, 12 years ago. People in the field of quantum information were saying, oh, there's no entanglement in these NMR system with a small number of quantum bits, so it must be classical. And then implicitly what they were assuming is that entanglement means quantum, which indeed, if you have something which is entangled, then there's some quantumness in some form in there. But do we always need entanglement to call something quantum? And they were assuming yes. And we don't really know if this is correct or not. But we also don't know that it is not true. And this was a challenge to the people who thought entanglement is equal on both sides to quantumness. Because here we start with a system where one qubit has a little bit of polarization and all the other ones are totally mixed. And then we show an algorithm where we start with one qubit with a little bit of polarization, everything mixed, and we do just a control unitary gate. And we go and measure in the first qubit. And what you find out of the measurement is that you're calculating the trace of these Cu. And it turns out that it's very hard, classically, to find a trace of a generic unitary transformation, even if U can be implemented efficiently with 1 and 2 qubit gate. So that was the idea of doing this. So sometime you might look at your physical system, it behaves differently than the ideal quantum computer, but you might still be able to do something interesting out of it. So this was a side remark on initial state. Yeah?
You're keeping the particle number 6. In your definition of rho, why is there no chemical potential?
In definition of low.
Usually it's 1 minus beta h plus mu a.
So in NMR, there's no chemical potential. I'm not sure why. And yeah, I don't know the answer then. Okay, so we've gone through initial state, a few things about noise. I'm going to say enough to make comment about the error correction, but not totally so that I will answer the question of exercise number 1. But with this, you should have a few hints. So I mentioned T2. T2 is the dephasing or decoherence, is the randomization of the phase of the qubit. That is, if you have a state which is alpha 0 plus beta 1, decoherence, or this T2, is randomization of the relative phase between 0 and 1. So if you have a little devil on the side who start to switch the phase here and kind of play with it, then you lose the quantum coherence of your system. And this is what T2 is able to, is measuring. That can happen either if this magnetic field start to vary, then you'll get something which looks like this. If the molecules who are nearby with the dipolar interaction, which are not totally refocused, comes in, you'll get something like this. If you have a molecule which is large enough that you have the wrong coupling between them, then it will look like a decoherence like this. And so if you evolve the system, what happens is that the off-diagonal terms starts to decay. And you can measure the rate at which they decay. You get T2. In the Bloch sphere picture, if you start with a family of pure state which covers the Bloch sphere, if you do a generic unitary transformation, it'll be a rotation of this Bloch sphere, so a solid rotation. And we've seen yesterday that you need 3 numbers to do this. Now, if you have only the decoherence of this form T2, what happens is that the sphere becomes like an American football, or maybe a rugby a ball for the people who play rugby. The state 0 and the state 1 is not affected, but superposition kind of gets squished in the middle. Now, in exercise number 1, what I want you to think is, if you have a generic evolution, non-unitary evolution, what is the shape of that football or ellipsoid? And how many parameters you need to characterize it? Okay. I should mention the T2 is typically 10 seconds. 1 second in system that we have. Between tens to hundreds of milliseconds up to 1, 2, 3 seconds. Other noise that we have is T1, which is the relaxation. So you take your spins, put them up. How long does it take to come back up? And so there, it's a little bit more complicated to see the effect on the density matrix. But you can figure it out from, again, this Bloch sphere picture. Again, starting with a sphere, you end up with some football, but it's not centered on the unit matrix anymore. It's kind of a little bit off of it. And then how much off of it depends on what is the temperature that you have. So then you have a slightly different flow, which is not totally symmetric, or a slightly less symmetry than you have. Okay? You remember also I asked the question on the noise on the exercise 1, why do we have only 2 parameters, T1 and T2, when we describe NMR? I've given you a hint a few seconds. I'll give the answer at the end of the lecture. Okay, so we've talked about noise. I'm going to go back to exercise number 2 and tell you how to do a control knot, because when we do the exercise on the error correction, then we are going to use this control knot. So you remember the control knot is the gate, and if the first qubit is in a state 0, nothing happens to the second qubit. But if the first qubit is in state 1, we call it the control, then the target qubit gets flipped. Okay? So one way of writing that gate is, you could write it that way. If the first qubit is in the state 0, the second qubit, you do not do anything to it. If the first qubit is the state 1, then the second qubit gets an X operation on it, which flips the qubit from 0 to 1, or if it was a 1, brings it to 0. Okay? So here I wrote it in terms of the states. Here I write it in terms of operation. And our goal is to write it in terms of NMR language. So you remember we have 1 and 2 qubit gates. And we have a 2 qubit gate, which we're going to use e to the minus I pi over 4 of Z1 and Z2. And this, up to some phase, looks like something like if the state, this one is 0, the first qubit is going to have a Z rotation, and because I have a pi over 4, it'll be a square root of Z. And then if the state is 1, is the square root of Z with a minus, because it goes the other way around. And we want to use this plus 1 qubit gate, and then try to end up with this. So the first thing that we want to do is to multiply this by a Z on the second qubit, so that becomes a 1, or the reverse of this, and this we get, let's say, a minus Z here. We want to change the phase here, and it turns out that this piece here is going to change the phase, and what we would left here is a rotation not around X, but a rotation around Z. So how do we change a rotation around Z to one around X? Exactly. We've done this already here, and this is what this sandwich here is about. Okay? So this sandwich is changing the rotation around Z to 1 around Y. Sorry, a 1 around Z to a 1 around X. This one, I should have been better and bring it here, and it changes really the phase which is there. By flipping this here, this can turn into a Z, and this one change this half to something which is full. So, okay, again, I'm being very quick at doing this. It gives you the idea of how related these gates. There's only one way of really understanding this, is sitting down and show that you get the right thing. I should make one note, however, is that the control knot here compared to this is this up to a global phase. So you'll get a phase on top of it, which is irrelevant. So you can forget about it. Now, once you have this, here's the pulse sequence which correspond to this. This is only for some of you who've done an MR. This thing means take a rotation around C2 by 90 degrees, and then the SP9 is a shape of a pulse that to do a certain operation, so that you want to do this in a certain way. I'll come back to shapes of pulse later on. But now you know how to do a control knot. I'm going to show you, if you go to the spectrometer, what do you see at the spectrometer? So what we're going to do is we're going to use a small molecule, chloroform, hydrogen, carbon. And we're going to use the carbon as the control, the hydrogen as the target. So if that state is 0, nothing is going to happen to that one. If that state is 1, we're going to flip this one. We're going to look only at that atom, the hydrogen. And this is what you see. I've put one in the state 0. You remember, usually you would have seen 2 peaks because they are coupled. There should be another peak here. Oh, things are not perfect when you do experiments. That peak would be here. A little bit. It's not exactly only the 0 state. There's a little bit of 1 state, but it's pretty good here. So you have the state 0 on the carbon, and then you're going to make this gate. What are we going to see? Is it going to change? So what I do is that I do the control knot on this with the carbon being 0, hydrogen being a target. I don't see anything. I shouldn't see. I do this. Here's the answer. You haven't seen anything different? Pretty much is the same thing. Indeed, the spectrum has not changed. So it works. Now what we're going to do is make the second qubit, the first qubit, the carbon in the state 1. So now it's going to flip the spectrum on H to the left, and we're going to have this. And now we're going to make a flip, if this thing works, and indeed you see the spectrum flipping by X. So by this you've made your first quantum algorithm in an MR, you've done a control knot. And if you remember also, the control knot is adding these two numbers and giving the answer here. On the last qubit, it's adding modulo 2 without the carryover. Well, you've added 1 plus 1 or something like this with a small quantum processor. Your first algorithm. Yep. How do I decide which one is the control, which one is the target? I know to do a control knot, I need to do this sequence here. So when I want to have the... Yep. Yeah, exactly. So when I want to have a control knot with the control on the carbon, it will mean that I will, at this moment here, I'll do the Z rotation on the carbon, and at the moment here, I do the Y rotation on the hydrogen. And this Y rotation on hydrogen means I send a current at the frequency of the hydrogen.
Right. Yeah. That's how you can select.
That's it. That's how I select which one.
It's slightly different from other systems, for instance, where you actually deal with the system. Whereas here you are controlling it from.
So I don't think it's that different. In an ion trap, you would take your laser and you shoot on one ion to do a 1 qubit gate. Here, instead of being in physical space, I'm in frequency space. I'm going to shoot at that frequency. And if you can make that leap, then you're okay. Okay. Very quick.
How much is the fidelity for this gate?
I don't remember, but we can make it at 0.99 roughly. If you look at 1 qubit gate, and we look at our best system in NMR, and we say, how good can we do a 1 qubit gate is 1 part in 10 to the 4. Okay. Now, this is on a molecule with 1 qubit. If you have many qubit in there, it's not going to be as much. But if you come to my talk on Monday morning, you'll have exact example of how much fidelity we have on certain gates. How do we benchmark devices in this? So good. And that's another advertisement for the other ones who are here. If you're coming to the conference on Monday, then you'll learn more about this. Okay, just a few words about, right now when I said you put a current here, what I have in my mind of a certain amount of time, usually people would say, okay, the current put in there should go like this, and for a certain amount of time in doing this. Now, when you go in the real world, making square pulses like this, it doesn't happen. So these things there's all kind of wiggle like this, it goes up and it wiggles like this. And then sometimes it's better to have a shape which is smoother. And so we use some of the smooth shape. And then, because of a Fourier transform between frequency and time, if you have a smooth shape with the time, which is delta t here, there's a 1 over delta t or delta omega spread in here. So if I have 2 qubits and I want to act only on that one, you need to know that you have a frequency which is small enough, spread which is small enough, which means that the time of this pulse has to be a certain thing. So there's a relationship between the two. And so you have to start to shape your pulses in a different way. And by shaping pulse, you can do something which turns out to be much better than doing square pulses. And this is something which is being taken up by all other implementation of quantum information processing. Shaping your pulse is critical to get high fidelity. I don't think you can get high fidelity by making square pulses. I mentioned yesterday that we don't really do Z rotations. We just push them at the end. And so if you have 1 qubit, it's easy to push them at the end. When you have 12, it starts to be really hard. So we wrote a small compiler which takes care of this. It also takes care of, you remember this refocusing, turning these coupling to 0. We know how to do this with these LMR matrices, but it's painful to do this by hand. It's straightforward, but painful. So now we have a compiler who does that. It also takes care of the thing, when we do these 1 qubit pulses, I should have mentioned this, they're very short compared to the time for a 2 qubit gate. So when you have 1 qubit gates, this is about 1 microsecond to 1 millisecond, let's say. Okay, and this is probably 10 millisecond to 100 millisecond. So for a good first approximation, this is instantaneous compared to this. And that's okay when you want to have a fidelity of 1 part in 10 or 12 or 100. But when you want to have a part in 1,000 or 10,000, then you have to take into account that when we do 1 qubit gate, there's a little bit of a 2 qubit gate that happened there. And that one you have to refocus and turn it to 0. This program takes care of this. So we can analyze and mitigate some of the errors by doing some of this. Okay. Whoops. So I finished with the noise, and now we're going to go and do error correction. And I have till what time? 12? Half an hour? Should be good. Yeah. Then I have plenty of time. The food for thoughts might be more on the food side than just the thoughts. You're lucky. Okay, so now I'm going to stop for the next 15 minutes. I won't talk about NMR. I will talk only about error correction. But I'm going to motivate it a little bit about NMR. Every time we do pulses, then they're never perfect. So we want to be able to correct for these imperfections. Because if you don't correct for imperfection, suppose that I do 1 gate, and the probability of success is 1 minus p. Probability of failure is p. So I do 1 of them, I get 1 minus p probability of success. I do 2 of them, and let's do something which is simple. I assume that the errors are independent from gate to gate. Do 2 of them, this will be squared. 3 of them, cubed. N of them goes like this. So if you don't take care of errors, the probability of success as a function of number of gates goes down exponentially. And if you don't have something like error correction, it's useless to have a quantum computer. Maybe for a few gates you might be able to do something interesting, but you won't be able to scale. They're going to kill you. And they said, we don't know how to make robust quantum transformations. And the idea of quantum error correction is to show that this is not true. But to do this, you need to have a few assumptions that the noise is certainly reasonable in some ways, and that's what the motivation of some of my work. But what I want to do now is to show you how you don't necessarily get that decay. How do you change it? In order to do this, I'll go back to the classical case. So I'm assuming that you've heard about error correction a little bit, or I'll kind of review some of these ideas, but I'll go relatively quickly. So the setup that we'll do is very simple right now. We'll assume that I want to send you a bit, and I want you to get it with a certain probability of success that is not going to fail too much. And this qubit is, have you passed your exam or not? And you have a job at the end, so you want to be sure that kind of, if you have passed, then you get the right answer, then I don't flip it around. So for me, as the prof, it's very important to be sure that you get the right answer. So you have some bit, I want to set it to you. So it's a little bit, if you think about quantum computation, it's a bit being in memory. And then you can deal with the bit you want to quantum compute right now. But it's simpler to just think about the memory right now. The ideas are there, and then you can build on this. So I have 1 bit, classical bit, and probability of reaching u, if I send a 0, let's say it's 1 minus p, probability of failure is p. For 1, it's 1 minus q, probability of failure is q. So it can be different between 0 and 1. So this defines my error model. It defines what can go wrong with my classical bit. For the rest I'm going to talk about, I'll assume that p is equal to q, just for simplicity, but you can go and do the whole thing with p different than q. Okay? So p, probability of failure, 1 minus p probability of success. So I want to send you that bit with a little bit more resources and ensure that the probability of success is better than that. So here's what I can do. Here's the simplest error correcting code. Instead of sending you a 0, I'm going to send you a triplet of 0. Instead of sending 1, again, I'm going to add 2 bit on them and just kind of flip them depending on if I have a 0 and 1 and send you the triplets of 1. And then I'm going to get the qubit, the classical bit, and I'm going to take the majority. I'm going to go and look at them, and then if I get the majority of being 0, I'm going to reset the bit to 0. And if I get the majority of 1, then this is going to fail what I'm going to try to do. But if you look at this, you realize that if I flip this back to 0 here, this happens with probability which is at most p. So the probability of failure was p, but now by doing this, I get rid of the probability which is proportional to p. Let's assume that p is small. It's going to fail, but it fails with probability p squared now instead of p. And because I've added a few bits, it fails 3 times p squared. Okay? So initially I had probability of p. I had 2 classical bits, and I do this trick, and then now the probability of failure is 3p squared. Now if p is large, this is worse. But if p is small, if p is smaller than 1/3, I gain by doing this. Okay? And so let's say that p is 1/10, then I'm more secure that you got the right thing. But you say to me, I want to be sure to 1 probably in 10 to the 4. So what I'm going to do is I'm going to use this idea of this code. That's here. So I took 1 bit, I encoded in 3. I'm going to do the same thing, each of them, I'm going to encode them in 3 again and go and calculate the right thing. And then if this was cp squared, in the case here c was equal to 3, then you go and calculate the probability of failure here. It'll be c to the cube and p to the...
So in this case, how to set your measurement? What are you measuring finally?
So I measure all the bits,
And
I take the majority. Okay? So I'm going to do this, and what you get is that with the first hierarchy, you get c. So here we get cp squared. Second one, we get c cube. And I think it goes up twice exponentially, so I think it's p to the 4th. Okay? Now, the first thing you look at this is that if I do this, the amount of resources go up exponentially because I triple every time. But this goes up twice exponentially, so I gain by doing this. So if you tell me I want to have a probability of success 10 to the minus 4, I'm going to say you need 2, 3, 4, 5 hierarchy of this, and then you'll get the right thing. And then you'll have successful transmission to the probability that you want. And this is the idea of classical error correction.
Can you again remind what C was?
Okay, C depends exactly what is the code that I'm using here. Okay? So here is how many times the p square fails. And it turns that it's 3 times because I have 3 bits. Okay? In fact, if you go and do the real calculation with the other terms, C will be equal to 1/2, but on the first order, if it's small enough, then it looks like the 1/3 is the right number. Okay? So, but C is the number. So if we have this, if P is smaller than 1/c, then this idea works. And you remember yesterday I talked about the accuracy threshold theorem, and there was a threshold. Well, this C gives us the value of this threshold, of when it works and when it doesn't work. So what we want to do now is do a quantum version of this. So to do the quantum version of this, we first have to think about what is the noise. Now here's a problem. That in the classical case, the noise was a bit flip. We were going to 0 to 1 or 1 to 0. In quantum mechanics, we have the Schrodinger equation. So if the noise is small, instead of having a wave function which kind of goes there in Hilbert space, maybe there'll be an epsilon here. So it seems that the error is not discrete, but it's continuous. So it's not a digital system. It looks like an analog system. And we don't know how to do this for analog systems. In fact, that's why there's so many devices today which are going towards the digital world. It's because it's easier to make them robust. So how do we go and do this? And the answer is this. Suppose that I have a qubit of this form here. And suppose it then interacts with the rest of the universe, which I call the environment. And then look at a generic evolution of that qubit with the rest of the universe, which is going to corrupt my system. Okay? I'm going to rewrite this equation in this way. So psi is the state. And so I put this one, and I put all the terms together. And I'm going to rewrite it in a way which is useful for the way I'm thinking. You can rewrite it, and I suggest that you do this as an exercise, in the following way. You'll have first the state that you started with some kind of environment. And then you have a state with the X operator in front, a bit flip, like a classical error, with a different environment. And then you'll have a third way with a Z. And remember that what Z does, if I have the Z on this state, what does Z does? That's it. This goes to alpha 0 minus beta 1. And this is a phase with a value of pi. Okay? And then you have a combination of both of them, xz. You remember that xz is equal to iy in terms of Pauli matrices. And so I rewrote the evolution of this quantum system in terms of nothing has happened to my state. A classical error has happened to my state, a bit flip. A phase error has happened to my state, and a discrete phase error, one with value of pi or minus sign, and then a combination of both. And this will always work because these are bases of operator in that space. And now I can start to think, oh, instead of thinking about the error in this way, I think about the error as either have an amplitude of having the right state, an amplitude of having a bit flip, an amplitude of phase flip, amplitude of both of them, and that becomes discrete. And I can start to think about doing something which is similar to the classical case. Okay, we had redundancy here. So the way I've done this classically is I said, oh, add two classical bits. And then copy the value of the first bit to the next two. So here I added my two classical bits and then copied, which is 0. But here, when I have a 1 first, I copy them, I get 1 and get 1 there.
Why 3?
Sorry?
Why 3? Why not 2 or 4?
So in the classical case, it doesn't work with 2. Okay? So you can detect an error, but you won't be able to correct it. Okay? Why 4? Why not 4? Because with 4, if 2 of these things flip, I take the majority, I cannot get a majority. You could get 5. 5 would work. In fact, 5 would work, and instead of a square here, you would have a cube. And so you could correct for 2 errors. So classically, you can go and do this. Okay? So,
It's very expensive on qubits.
aha, very good point. We need more qubit, or here it was classical bit. So it's more. But I've told you that the error probability decrease exponentially with a polynomial amount of bits. So I've gained doing this. And now, how much do we gain? So when I started to learn about this, I was in Santa Barbara in the mid-1990s. And people were thinking about large codes. And I said, why are people interested in large code? And it turns out that people who use CDs, or maybe you guys are too young, you use MP3s nowadays, but in my time we use CDs, and if you go mountain biking with your CD, it usually doesn't skip too much. It doesn't skip too much because of error correction. And they have codes which are thousands of bits that people are using. So these large codes sometimes are very useful. And even if they are expensive, if you get the right answer at the end, you win. So maybe instead of passing your exam, maybe I should say you get the Nobel Prize or you don't get the Nobel Prize. There the accuracy people would be more happy with this. Okay, so the next piece I wanted to mention is how do you do the... I mentioned this here that I copied the information, but in quantum mechanics you cannot copy the information. There's something called the no cloning theorem. So we're stuck. In fact, the Landauer and Unruh knew this, and that's why they thought quantum error correction would not work. So it turns out we're going to use something slightly different. Well, trying to move the information in the Hilbert space in a different way. So that if an error occurs, the states that comes out of different type of errors don't overlap with each other, so we can trace back which error has occurred. And although it seems a little bit nebulous to you right now, I'll give you an example in a second of how that works. And in that way, if we can trace back which error has occurred, we can come back and find what happened to our state and then correct for it. The last thing is that if I had an error, let's say the classical error on the second bit, I told you to go and measure the parity, to go and measure the majority of this. So you measure this, you measure this, you measure this, and say get 0, 1, 0. Or if here you would measure 1, 0, 1, then you would kind of reset this. If you get this, you reset this to 0, get this, you reset this to 1. But if you do this quantum mechanically, by measuring that bit, you're going to collapse the state either on this side or on this side. So you lose your quantum information. So you cannot measure the bits themselves. But it turns out by looking at this, you can know that an error has occurred without collapsing the state. What you're going to do is that you'll make a measurement which measure not the value of the bits, but the parity of the bits. So you're measuring, are they different? And you see that here, these two are different. These two are different. The value of the bits are not the same, but the difference is the same. And if you measure this, you don't collapse. And then you can keep the quantum information. I'll show you how does that work in practice. So the objection to quantum error correction was the noise was continuous. It was like analog. Well, I showed you that it doesn't have to be the case. There was a no cloning theorem, and I'll show you there's a way around it. And measuring, instead of measuring the majority, we're going to measure parity, and this thing can happen. And that's where we're going to come back to NMR. So I first told you that the type of error that we can have quantum mechanically is the operator x, the operator z, and then x and z. But in NMR, the z error are related to T2, and these ones are related to T1. And we have typically look at molecule where T2 is much smaller than T1. So the dominant type of error are the z error. And so we're going to correct for that first. And after, later on, we can go and correct for x. So the first code that we need to find is to correct for z error. Now there's a hint about finding a code which works like this. Because you remember that if you do a rotation around the y-axis of 90 degree over z, a rotation of y, or 90 degree, the dagger, or we've done this here, z is going to transform into x. We know codes, at least we know classical codes, we correct for x. So the quantum code correcting for z should be related to the classical code with this transformation ry. Okay. So that's where I came back to NMR. I'm going to correct for Z errors first, and after that we're going to go and look at different case. Okay? So here's going to be the example of a 3-bit code which corrects for Z errors. But I need to add one piece. To be sure that you're going to follow me. If you have Z on the state 0, it gives you the state 0. Z on the state 1 gives me minus. So we're going to go, instead of the 0, 1 basis, we're going to go and look at the basis which is plus or minus, which is 0, plus or minus 1. Okay? If I take Z on plus, what do I get? And if I do Z on minus, plus. Now, if you live in the orthogonal world and you think, oh, that may be a 0 and this is a 1, this Z on plus is like an X on 0. It flips the state. And same for this. So we're flipping the bits in that different basis. So that's why the code seems to be very similar to what we have seen classically. And you'll see. So what we're going to do is first do this encoding that I talked about. So that's a unitary transformation. And so we're going to encode this by doing a control knot between the first qubit and the second qubit, first qubit and the third qubit, and then we're going to do Y rotation on each of them. So we do the first encoding between the first qubit and the second one, or the first gate, first control knot. So if I have this, alpha 0 plus beta 1 times 0, and I do a control knot between the first and the second qubit. The control is on the first qubit. I get something like this, right? Now if I do the same thing with the third qubit, we'll get alpha 0, 0 plus beta 1, 1, 1. Okay? And now I'm going to do the Y rotation. The Y rotation is going to turn this into alpha plus 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 beta minus minus minus. Okay? And then I'm ready. And then I told you that I had Z errors. And so there's one thing which I did not mention is if you have Z error for 1 qubit, how do you compose this for many qubits? We'll assume that the errors are independent between qubits as a first step. It's not a bad approximation. So for 1 qubit, I told you that either there's an amplitude of getting 1, nothing happens, or the amplitude of getting a Z error. So, and let's say that the probability of this is gamma, or P. Now if we have 2 qubits, then there'll be a probability of having 1 error, 0 error, 1 error on each of the qubit, and then 2 errors on 1 error on each of the qubit at the same time. And then if you have 3 qubits, you have the probability of the 0 errors, only a single error on qubit 1, 2, or 3, then 2 errors, the different combination, or 3 errors. Okay? To lowest order, we'll have errors which are only a single Z on each of the qubits independently. So this is what we're going to do. We're going to say the decoherence to the lowest approximation on the probability of error. What we're going to get is, so the error model is either nothing happened, so this is unit, unit, unit on each of the qubit, or, and this is 1 minus gamma, or P to the power cube, and with probability P, and I use gamma because for some reason in that slide I put gamma down there, so P and gamma is the same thing here. So either I have an error on the first qubit, either I have an error on the second qubit, or an error on the third qubit. Okay? So if I have no error, well, the state that I got here remains the same. Okay? If I have an error on the first qubit, this plus here becomes a minus. I try to be clever. Okay? If I have the error on the first qubit, you get a minus here and a plus there. Error on the second qubit, a minus there and a plus there. And then error on the third qubit, you have a minus there and a plus there. Now notice that there's no overlap between this pieces and any of the other state. Okay? And same thing. There's no overlap between this and nothing else. So you can never mix up a state like this one, which has been which has not been corrupted, which has been corrupted, or the encoded 0 with the encoded 1 which has been corrupted. There's no overlap between two of them. So if there's no overlap, certainly we can trace back in some fashion, we'll show you how to do this, what error has happened. And we can trace back by measuring these parities. So how do we go and measure parities? So I make only these average if I wanted, or how do we go and do this? Well, one way of doing this is to take this code and invert it. So this is the decoding person. So if this is operation U, just do U dagger. And so if you do U dagger on this, what you'll get is, well, the top is going to bring you back to what you started from. That's pretty obvious because you do the dagger. Now the interesting case is, let's say this one. Okay? So we do the Y rotation. So minus is going to become a 1. And then 0, 0. And then a 0, 1, 1. And then we're going to do the control knot. So this now is a 1. So this will become, so this one is 1, 0, 0. So this is going to become, after the two control knot, 1, 1, 1. And if you continue doing this with the beta, is a 0. Here you had 1, 1, so nothing changed, you have this. Okay? Then you can do the same thing, doing the inverse for these two states. And you get this here. Okay? And it turns out that the parity between the first two qubits is given by the first column here. And the parity between this one and this one is given in the second column there. And if you go and measure this, 2 qubit here, then you're not collapsing that state here. Right? And so, in fact, you don't really have to go and measure, because if you look at this code, the only thing that has happened is when there was an error, which was in the first qubit, it have imposed an X on the first qubit. And here, even if an error has occurred, it hasn't affected my first qubit. So I got the right answer here, 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 and here. But here I have to make a correction. And I have to make a correction which depends on the value of the last 2 qubits. And when the last 2 qubits are 1, I want to do an X. So you remember we did a control knot? When there was one value of 1 here, I was doing an X. Here I have a control knot. It's called a TIFR gate. It's written in this way. So a control knot was a control little dot here. That's an X rotation. Here I'm going to have a control knot gate. Okay? And by doing this, then this one is going to flip to 0 and 1. I'm going to recover the information that I wanted. And so you have error corrected. How well have you corrected? Well, we've corrected for 1 error. So only one of those. But certainly at some point you have a chance of having 2 Z's. Z1, maybe Z3. But this will occur with P squared. And so we would have, if you go into the whole calculation and say how well we've corrected, so instead of being the error being P, if you would not use error correction, we get 3 gamma squared, which is very similar to what we had before in the classical case. It's not exactly the classical case because we've done these measurements in a slightly different way because we're in quantum mechanics and we cannot calculate the majority by looking at the bit themselves. The noise is slightly different, but the idea is very, very, very similar. You just have to adapt it in the right way. So now you know.
I had a question.
Yep.
what happened to the environmental state which caused the decoherence?
So it's coupled to these things.
Yeah, so something else
Yeah.
has to appear, right?
Yeah.
But for each state, the environmental state is going to be different.
It doesn't matter.
It doesn't matter.
Yeah. So that's why when I said here we're going to use insulation, what we've really done is that we've taken our quantum state, which was on 1 qubit, we spread it on 3 qubit, and we change it where it goes in the Hilbert space in such a way that when the noise comes in, it doesn't touch the quantum information. And so that's what I meant by using insulation. So this was a naked little qubit. This is an encoded qubit where the noise cannot go. It's a little bit like a refrigerator. All right? We've kind of put a shell by using more qubit around our information qubit, and when the noise comes in, we go and make those measurements the right way and try to get rid of the noise before it affects the quantum information. And we know it affects it. If we don't do error correction fast enough, this term is going to start to affect us at some point. You know this. But similar to classical error correction. Okay, so
Are there theoretical estimates of P
yes.
in these big molecules models that you've been?
So people have made estimation of what P would be by looking at some codes, assuming some type of error model, some types of fault-tolerant method, etc., and then you get some values, and the values are related to what the assumption they're making. The typical values that people got initially when I was involved in that work 10 years ago was 10 to the minus 6. Last 10 years, people have improved it to 10 minus 4 to minus 3 by proving rigorous theorem, and by making simulation, which seems reasonable, people get values to 10 to the minus 2. And there is just a simulation, might be okay, might be not. But it always depends on what the assumption you have. Change your assumption, you're going to change this. One thing that I haven't mentioned up to now is that I assumed that our quantum information was in the memory of a quantum computer. But in general, you want to compute with it. So when you compute and you transform, what do? Second thing is I've made the assumption also that when I encode, I don't make any mistake. The mistakes happen only in the red part here, and when I decode, I don't make any mistake. So in general, you have to take into account the possibility of making errors here and making errors here. And by this, you need to add some piece on the circuit here which checks to be sure that the gates that you're doing are not making error. And I erased this value of P. I had this thing called P is smaller than 1 over C, where this is the threshold. Assuming that the thing is classical, we had a value of C equal to 3. If it's quantum, and I don't make errors, I get also the same value. But when I start to make errors, and I want to make these operation fault tolerant, I'm going to change the value of C because I have more gates that I have to do, more qubit to add, more complexity. And this is by calculating this value of C, we get the value of this threshold P, which is of the order of 10 to the minus 2 to 10 to the minus 12, depending on what assumption that you want to do. Okay?
Well, one more question I had, which I think is
Yep.
quite relevant. What
Yep.
are the time scales that you use to encode and to decode?
Very good question. So you want to do all of this, all your operation at time faster than the error that comes in. Because if the error happens faster than what you can control your system, then you cannot do anything.
These time scales actually faster than the decoherence time.
Yeah. So, but to be very precise of how much, you go and look at a physical implementation of this, and this is what we're going to do. Okay? So, yeah.
We are assuming that the noise changes the qubit. The noise changes the state by changing the qubit, right?
The noise changed the information on the qubit.
Yeah. But let's say it changes the amplitude.
Yeah.
The whole state itself. It deforms the amplitude. I mean, it doesn't really change 0 to 1, but what it does is changes alpha to alpha 1 or and beta to beta something else. And then it's a difficult, though it may be invertible, we have no idea of how much, what it has happened. We can't keep track, right?
No, we can, because you remember so this is the generic evolution of 1 qubit. So you're changing alpha to alpha prime, beta to beta prime, and you're even changing the coherence on the Bloch sphere. So you go from one place on the Bloch sphere to some other place on the Bloch sphere. And I've described this between nothing happened, x, y, and z. So it takes into account of this. Now what I haven't done is that right now I've shown you a code which corrects for only z error. Well, because of this duality doing a y rotation, if we have only x error, same code would work with just small difference. But what happens if you have z and x error? I'm going to give you that answer in a few minutes. But before, I'm going to answer your question. So here's the circuit. Maybe I should have. I now want to translate this in terms of NMR. You were wondering why I asked you to do a control knot. It's because we're going to use it. So we've shown how this works. We're going to change this. We know how to do this. This Y rotation, we want to do this. We need to do this control knot also. The Toffoli gate. This is not a 2-qubit gate. It's a 3-qubit gate. But our friends, the computer scientists, told us that we can always do a 3-qubit gates in terms of 2-qubit gates and 1-qubit gates. And you're lucky. I'm not going to give you that one as an exercise where you would have to solve it before dinner. I'm going to give you the answer. So if you have a gate which is control v squared. So v squared here is x because it's a control knot. You can rewrite it in terms of 2-qubit gates in this form. So you can just write this and then you can go and make this happen. So in our case, instead of being v here, it'll be the square root of x. And then you can go and find what it looks like. So this is what the circuit looks like. This is the decoding of this part here. So x rotation on the qubit in the middle, a y rotation, a ZZ coupling of I pi over 4, y and x. And I don't think that's that illuminating to go and look at this, except if you want to go and really see how it works in details, you just add this, and you'll see that this makes a control gate. And you'll realize that compared to my previous slide, the control here are up and down, and this is because we had a molecule, a 3-qubit molecule, and it's easier to do this Toffoli gate in a certain way, so we kind of just optimize it in that way. So here's the answer to your question. How well do we do? So you remember what we're interested in is if we don't do anything with a noise, the error, when it's small, will be linear in the probability of error. This is the red line that we have here. So if we do the encoding but don't know the error correction, it's going to decay exponentially. If we do the error correction, what we see is the curve, we start a little bit lower, I'll explain why, but it flattens up. And you can make a estimation of how much it's flattened up. I'll show you it on the next slide. And then we show with this that we've reduced the probability of 1-qubit error by doing the encoding. And so in that case, we have a certain amount of errors when we do the encoding, we do the decoding. This is why this doesn't start at 1. Doing encoding and decoding makes some errors. So if we do the Toffoli gate, the last gate, this is the difference between the red here and the green one. Okay? But we do show in the simple molecule here that we can improve it a little bit. So we have enough control to show first step of quantum error correction. The experiment I just shown you, this one here, was done about 10 years ago. And in the last 10 years, we've improved quite a lot of the control that we've had on the small system. And I would say the greatest progress we've seen in experimental quantum information science in the last 10 years is not increasing the number of quantum bits that we have. We have about a dozen of them. That's the best we can do at present. But the amount of control has increased quite a lot. And this has been quite an achievement. And here's an example of this increase of control. So here's the plot of this line here in red when 10 years ago. So we don't start at 1 at time equals 0 because we do some gates, we lose some signal, and it goes down linear in t because we don't do the error correction. When we're doing the error correction, then we start a little bit lower down, as I mentioned, but this term's proportional t is much smaller. And this is the demonstration of error correction, or that we have the control of error correction. So with more control, a year ago, we did the same experiments. You can see that we started now with much better fidelity at time 0. So only 1% in doing this gate, all those one, and not the TOEFL, because it's a little bit longer. Well, we had only 1% error in doing all these gates. And if we do the TOEFL gate, then we have 2% error. So 1% error of this, well, a little bit more complicated gate. And we can see also that the first term has decreased dramatically. So the increase of precision is a factor of about 20 compared to what we had about 10 years ago. And this shows how we can do error demonstration that we have the control for quantum error correction. Okay? One pitfall of this experiment is you see these zeros here. Well, we've done this with the pseudo-pure state, this initial state, and this takes up some signal. So every time we add 1 qubit, the signal divides by 2. So if we could have real zeros, we would have demonstrated quantum error correction, but we don't. So this is something that an MR has to do, and we don't know how to do this with liquid state MR. But with solid state, by using an electron, and this algorithmic cooling I mentioned a little bit earlier on, we might be able to reach this, and we know that we have the control of the nuclear spins to demonstrate full quantum error correction.
What enables you to have better control now?
We did not have this RF selection in the experiments here. We also have shape our pulses. We have so these two things, and this compiler that I mentioned, who takes care of errors when we do 1 qubit gates. So nothing dramatic, but a bunch of small things which suddenly kind of start to count.
Are you using grape here?
Yeah. And I was not going to add this. Here's the expert who knows very well about grape. It's a way of shaping these pulses in a way where we can increase the amount of control dramatically.
By the way, what is grape? I'm not familiar with the word grape.
It's a different type of grape. It's a way to shape pulses in certain way.
Shape pulses, but what exactly it stands for?
Gradient essence pulse engineering.
Oh, I see. Okay.
And sorry for the rest of the audience. I'm not going to go down there. Here's an experiment.
In our laser physics also,
Yeah.
we shape the pulses all the time.
Yeah.
We just call them shaped pulses.
That's okay. Here's an example where we've done twice error correction. So we've done a first error correction, then decode, error correct, and then do it again. So because you do more gates, for a small amount of time we don't gate, but for a larger amount of time you start to gain by doing this. So no error correction, 1 round of error correction, and 2 rounds of error correction, we can do this. So it shows the fact that we've crossed that little piece here shows that we have enough control to do 2 rounds of error correction. So my goal is to do many rounds of error correction so that we can keep that quantum information for long enough. So we are slowly getting there on the control part. Okay, somebody mentioned what happened if we have something else than the errors. If we have X error at the same time as the error, that the code with 3 qubits is not sufficient. We need a code with a larger number of Encelad's extra number of qubits. And it turns out that the smallest code has 5 quantum bits. And so I'm not going to go into details, but just know that if you have more types of error, means more complex code, and more complex encoding. So remember, for the Z error only, you had 2 control NOT and the Y gate. Here's what the circuit looks like. And these circuits, this one followed by this, is the equivalent of the TIFR gate. It corrects for the type of error. So something which is more complex. Despite of the complexity, we were able to implement that code and show that if we induce error by hand, in this case, we could correct them. So again, we have the control of making these things happen. Okay. How am I doing with time? I ran out? Okay. So I'm going to jump to the conclusion. If somebody's interested in algorithmic cooling, I can talk about it. So what you've learned in my 2 lectures, first one is the use of nuclear magnetic resonance for manipulating quantum information. So you know what are the qubits, the nuclear spins. We can manipulate them with 1 qubit, 2 qubit gates. How we do this? The 1 qubit gates are done with sending radio frequency pulses. The 2 qubit gate is a natural interaction that comes in through mediated by the electrons. And we can control these systems really well enough so that we can implement basic or first steps towards quantum error correction and be able to demonstrate that we have enough control today to kind of show gain by doing error correction, assuming that we have the initial state in the state 0. This is something that we wish we will not be able to achieve with liquid state NMR, but with solid state NMR, maybe nitrogen vacancy centers, we'll be able to use the same techniques that we have and then implement it there. Liquid state NMR will not be the final way of scaling for large quantum computers, but it's a very good system to learn how to do quantum information processing. And the techniques that we've developed in there has been used in many other areas, being ion trap, nitrogen vacancies, quantum dots. And so these techniques can be applied other places because in NMR we have such exquisite control on the spins that we are ahead on anybody else on the control. And then we can match with other places so that we can get scalability on devices. There's no way that we can think of scaling up without some form of quantum error correction. And my second part of my presentation was related to this. And I hope you've learned the basic ideas of a quantum error correction. I don't expect you to know all the pieces by heart, but at least you've heard the basic pieces, what are the tricky part, what are the difference between classical and quantum error correction, and then you can go look at the lectures on the web and kind of play with the first codes, and so with this you can build your intuition of how it works. So thank you very much, and I'll be happy to take some questions. Yes?
What about adiabatic quantum computation? Do they still require error movements?
It's a very good question. So the question is, with adiabatic quantum computation, do we need to have error correction? And the answer is we don't know. And we don't know how to implement error correction in adiabatic quantum computation. For the people who do not know what adiabatic quantum computation is, it's the idea of, instead of computing by using gates, the way that we have here, what we're going to do is to change the Hamiltonian slowly. Where, let's say that we can solve a problem if we're able to implement a certain Hamiltonian H. And we know how to reach this from an Hamiltonian H0. So if we write an Hamiltonian which is of this form, yeah, thank you. So suppose that we have a final Hamiltonian we want to reach. We know the initial Hamiltonian by slowly moving, changing the Hamiltonian from lambda equal to 0 to lambda equal 1 to this one. We do this slowly where we can reach the ground state of this Hamiltonian. And the answer of our computation is the ground state of this Hamiltonian. By transforming our Hamiltonian from H0 to HF in an adiabatic way, we're able to kind of get the answer of our quantum computation. The question for adiabatic quantum computation is that can we do this in an amount of time which is not exponential on the size of the problem that we're interested in? And we don't know if this works for generic quantum computation that we can solve with the gate model. If we can do this, and there's no error in the control of the Hamiltonian, then indeed we will end up in the ground state there, and we don't need error correction. But the question is, what happens if we don't have perfect control on these Hamiltonian? What happens then? And if you take an Hamiltonian, a generic Hamiltonian, and you look at between the ground state and the first excited states, in typical one, the space level between these two will typically decrease exponentially as you increase the number of qubits. So by suddenly kind of having errors in the Hamiltonians, it might become harder to do this, or it takes an amount of resources which can go up exponentially. So we don't know the answer to these questions, and they are really interesting ones.
Okay, so as you say, quantum error correction will be necessary to build quantum processors. Given a particular implementation, so experimentalists report things like the fidelity of the gates, et cetera, is there a way to take the experimentally reported results on fidelity, et cetera, then figure out if quantum error correction would work in the sense that concatenating it would converge? And do you have an idea of what would be the implementation that would have the smallest quantum error correction overhead?
Okay, so your question had many steps. So the first one was, people report some fidelity of certain gates. So if you report the fidelity of some specific gates, it's hard to make a general comment of what you can do in general. People have worked on what is called benchmarking. So we have a very good idea of how to benchmark one qubit gates, and we have getting a better idea of how to do it for multi-qubit gates. And if you come to my talk on Monday, then you'll get an idea of how this can be done. So there we can have an idea of an error per gate, which should be representative for what we need for quantum error correction. So that's the first answer is, I think we are getting there of understanding.
So you're saying that, yeah, in that sense, the benchmarking you're doing is sufficient for a person to determine whether quantum error correction concatenated would converge to allow scalable quantum computing. Okay. And then the next part was...
so if you have this value, what's
going to work now? Like, where are we with respect... Well, which implementation is the most promising at the moment for reaching the point where quantum error correction would deliver scalable quantum computing?
So there's no devices that we have right now which have demonstrated a sufficient control on more than one qubit gate. So all of them are rather poor still on demonstrating one scalability. As I mentioned before, a few minutes ago, we don't have quantum information processors with more than 10 quantum bits. And to implement error correction, we'll need hundreds and thousands of quantum bits if we want to have repeat error correction a few times in a decent way. So we're not there yet to think about scalability. So we're still very far from implementing full views of quantum error correction. Does that answer enough?
Well, this is related to his question actually. So what is the status of error correction in quantum optics, for instance? I mean, this is all about NMR, right? So it's a beautiful description of how it works in NMR. But does it work in other systems, and how well does it work?
So for ion trap or superconducting qubits, what I've said can be done.
Has it been done?
Yes. So again, come to my talk on Monday, and then you'll get that part.
I will try.
So I'm trying to. There'll be a lot of people. So For ion trap, people have done repeated error correction when they induce errors by hand. So they show that they have enough control to do this for ion trap and superconducting qubits.
But what about quantum optics?
For
What
quantum
about
optics,
photons?
things are a bit different because the measurement is destructive. You destroy photons, which you don't do in NMR, you don't do in ions, you don't do in superconducting qubits. So you
then
don't.
If there's no way, then I mean, then are you saying that you can't
is-
really use photons for anything useful?
I
Like,
didn't say
this,
there was.
This can also go to Professor
Okay.
Agarwal, actually. I mean, he
So-
can also have a.
You have
take
to
on this.
use slightly different techniques to
Okay.
make things happen. And the idea of linear optics quantum computing of my colleagues Manik Neil, Gerard Melbourne, and myself gives an example of how you can do this. But we're still, again, this takes a lot more resources than what we would need for NMR and ion trap or superconducting qubits. So to make things robust in general for optics will be harder because of the measurement is different.
Okay, thanks.
Also, photons fortunately are much less susceptible to decoherence. If you have a cleaner environment.
Absolutely right. So
So,
photon.
like Salinger, he went to this Spanish island because the atmosphere there is much cleaner and the photons can be sent over 200 kilometers or 300 kilometers without much decoherence.
Absolutely
So
right.
that's a great advantage with photons as compared to many other techniques.
There's a great advantage. In fact, the official for the quantum information science people, they use Zeilinger's experiments on the Canary Islands, where they've sent photon on 150 kilometers and show they don't decohere. But there's a better one if you look at astronomy. If you look at the microwave background, the fossil radiation from the Big Bang,
3 degree.
3 degree,
Yeah.
and you can see in it that there is polarization that has survived from the beginning of the universe to now, which is about 10 billion years, which means that these photons have not decohered. If they would have completely decohered, the polarization would have been wiped out. So here's an example of a qubit where the information was kind of given by the person who set up the Big Bang, and then came to us and is not decohered yet. Now, we cannot do quantum computing with those. But the problem that comes with photons is to try to make them interact. When we try to make the 2-bit gates, it is really hard. So the price of having low decoherence is compensated in some way on trying to make 2-bit gates, which become very hard. Again, in the LOQC system, there's a way of doing this.
You can inject a medium to do 2-bit gate.
It's too weak. So the Kerr medium makes gate, so we can, instead of a control not gate, an equivalent is a control phase gate. And so this is control not gate is equivalent to a control phase gate with a phase of pi. If we use Kerr medium, we get, instead pi, we get 10 to the minus 5 pi.
No, you will get that medium in a cavity in optical chemistry. Like Jack Kimball's experiment. Jack Kimball in 1990
Okay.
demonstrated essentially a phase gate using the high quality cavity cube.
Okay.
I mean,
So you can always push the problem one place to the other. And so if you get a cavity there, I think the error was, the phase was 17 degree instead of pi.
yeah, but this system
And he could do one gate. And if you ask him to do another gate, he needs to have another atom going to his cavity exactly at the right time. So
well, there are problems. I mean, in every
there are problems at many places, but there've been progress also in many places. So there are challenges, which is good for you guys. If there would be no challenges, it would be a boring field. There are great challenges to get.
That's why the younger people come in.
Absolutely right.
We are doing error correction because of decoherence, right?
Because decoherence or because of noise.
Because of
Any kind of noise that you would have in your system, you would need this. So decoherence is an example of this. Relaxation is another one. But also, at some point I mentioned how to make a rotation more precise. So just the calibration being imprecise can be corrected by using ideas of error correction.
Suppose the decoherence time is infinity. Suppose we make that decoherence time is infinity. So no need to worry about. So we can get correct information, correct?
Okay, so if the decoherence time is what?
If now we worry about decoherence time also.
Okay,
Suppose we make decoherence time is infinity.
infinity. So if the decoherence time is infinity, then you don't have to worry about decoherence.
Is possible to make infinity?
Well, I don't know how to make the decoherence time infinity, but if you know how to do it, then yeah. So you would have your system which doesn't interact with the surrounding at all. Then it would be very hard to control it.
So let's stop here because we have to go for lunch and then reconvene. We can continue discussing. There's a discussion session I think as you can make out at 4:15, so we can continue asking questions to all our lecturers. For the students, we are going to hand out the certificates now. So if you could just hang back a little bit. As I call out your name, just come and select your certificate and we can go for lunch. Okay. So let's thank Ray again for.